quantum coherent contributions to energy transfer.
Okay, so thank you for that introduction. So my name is Hallmann Óskar Gestsson, and I am a postdoc in Professor Olaya Castro's group. And so I'm very happy to have this opportunity to be here today and to share with you all some of my research on, particularly on how we characterize the quantum coherent contributions to energy transfer rates in open quantum systems. So we are mainly interested in biomolecular and photochemical systems that are involved in the kind of primary energy transfer steps of photosynthesis. And so these are, for these systems, it is believed that quantum coherence plays an important role with, and we want to answer how, so we want to design a theoretical methodology that will give us the answer to how much this quantum coherence matters to energy transfer, in particular excitation energy transfer. So yeah, here I have a picture of LH2, which is a typical example of a light harvesting antenna complex, but what I'm talking about is general, so it will apply to more other interesting examples as well. So a very natural figure of merit for an energy transfer process is the transfer rate, and computing the transfer rate for a system is a problem that shows up a lot in many different domains of study, so physics and chemistry and biology, where you essentially have a network of states that transfer to one another their populations according to some rates. And so what I have here a picture of is just a kind of pictorial representation of a master equation, but actually computing the transfer rates that enter into the master equation can be a very difficult problem, in particular when you have many multi-exponential processes occurring all in parallel, and you have non-Markovian effects you want to account for, and you have on top of that quantum coherent oscillations as well. So when it comes to quantifying the contribution of quantum coherence to energy transfer, the problem is really twofold. First, we have to actually have a nice, rigorous, and robust way of computing the energy transfer rate for a given open quantum system. And then once we have that master equation from that method, we can then have to determine how much the quantum coherence has actually contributed to that transfer rate. So in other words, we have to isolate the influence of quantum coherence to the energy transfer process. And to exemplify my proposed solution to this problem, I'm going to consider the dimer. So I have here a picture of a dimer of bacteriochlorophylls that couple to one another electronically. And we model this using an open quantum system where you have two subunits with two excited states that are electronically coupled to one another, and they are separated in their energy by some detuning, delta E. And then, of course, the molecular vibrational environment of the dimer is modeled by a spectral density. And so I'm going to consider two examples of spectral densities. One is the overdamped Brownian oscillator spectral density, and then one underdamped Brownian oscillator, which models a kind of well-defined vibrational mode then at 150 wave numbers. And so our baseline here is, so in order to kind of simulate the dynamics of this system, we use the hierarchical equations of motions, which is a non-perturbative approach to computing the open quantum system dynamics of these systems. And basically what you have here is a hierarchy of equations of motions. And at the top of this hierarchy is your reduced density matrix dynamics, which then are coupled to auxiliary density operators, which then simulate the influence of the non-Markovian bath that is influencing the reduced system dynamics. And as you add more tiers to your hierarchy, you get closer and closer and converge to the final correct solution. But so this is not in the form of a master equation. So we have to do a little bit of work to get the transfer rates. So just to kind of illustrate this problem here, I'm computing now the dynamics of the higher energy exciton of the dimer for the underdamped Brownian oscillator and for a fixed value of the electronic coupling at 50 wave numbers. And I've done this for 3 different values of the detuning. And so in particular, the dashed yellow line is the point at which we have a resonance between the excitonic gap and the vibrational mode at 150 wave numbers. And you can already kind of see that we can compare the transfer rates between these 3 processes, but it's not clear exactly what is the quantitative value of that transfer rate. We can do a fit, but how that fit will capture the oscillations can be tricky and is essentially approximative. But what is less obvious is what has been the impact of quantum coherence to these dynamics, right? So has quantum coherence actually improved the transfer rate? Has it suppressed the transfer rate, or is it irrelevant? It is. I mean, it's doing something, but what it is difficult to tell just from the dynamics. So when it comes time to computing the transfer rate itself, we follow this paper published in 2016, which essentially suggests using Nakajima-Swansek projection operators to map the hierarchical equations of motion into a generalized master equation. So we pick a projection operator onto the eigenstate populations, and then we can then derive and compute the memory kernel that describes the dynamics or the kinetics of the eigenstate populations. And this memory kernel contains all the information of how the vibrational environment and the quantum coherences have influenced the dynamics. And so you have these kind of, I put these formal expressions that we can use to compute the transfer rates. So they are formal, but like numerically tractable. So that takes care of our first problem. We have the transfer rates, the total, and then for the second part of the problem where we want to isolate the influence of quantum coherence, we propose the following decomposition. So we now have the master equation, which is described by a matrix here, K subscript Q. And we now want to decompose this projection operator further into a projection onto the vibrational degrees of freedom, which is this R, so R for reservoir, and then the projection onto the excitonic coherences, which is this C projection operator here. So doing a bit of algebra, you can actually show that this transfer rate can you can decompose it nicely into these 2 different components. So you can essentially write the total rate of transfer here as a contribution that comes from the vibrational environment. So the influence of the vibrational environment onto the eigenstate populations. And this is independent of quantum coherence. There's no quantum coherence that enters into this term. And then all other terms in this expansion will then be dependent on quantum coherence. And so this second term describes essentially the influence of environment-induced quantum coherence on the population dynamics. So that takes care of the second part of this problem. And so now, just like we can compute the total transfer rate, we can also compute thermal relaxation rate. Similarly, we just change projection operators. And so that means we can actually then compute these 2 different rates and take the difference. And there's this difference then that gives us the quantum coherent contribution to the energy transfer rate. And so we propose then this kind of nice figure of merit that kind of characterizes and quantifies the impact of quantum coherence to the transfer. So it is the difference between our total transfer rate and the thermal transfer rate relative to the total transfer rate. And so we can then just see that when this difference is positive, we have had a positive influence coming from our quantum coherence, and quantum coherence essentially acts to enhance the energy transfer. Whereas if this number is negative, quantum coherence has actually suppressed the energy transfer rate. And of course, if this is 0, there is no impact at all. So coming back to the dimer problem, or dimer dynamics I showed you before. So what I'm plotting here is these two transfer rates. The solid line is the total transfer rate as a function of the detuning of the dimer. And when you have the resonance condition at 112 wave numbers, you actually have a very strong enhancement of the rate coming from quantum contributions. As we can see, the dashed line is our thermal reference. And so there's a positive difference. Whereas in contrast, for the 50 wave numbers, you have a suppression because the total transfer rate is smaller than the thermal reference. And similarly, for the 200 wave numbers detuning, you still have a positive influence coming from the quantum coherence to the transfer process. And so if we plot the figure of merit corresponding to this result, you can see this quite clearly. So the pink area here is the area where you have enhancement, and the gray is where you have suppression. And you can see even at where we had the very small transfer rate, the actual relative contribution of quantum coherence is quite non-negligible. It's like accounts for 20% of the total rate. So now I'm going to move from the underdamped oscillator into the overdamped Brownian oscillator environment. And still the same dimer with 50 wave number coupling strength. And I'm going to look at the figure of, so I'm plotting here the figure of merit for the energy transfer rate as a function of the detuning again. And then the inset shows us these two rates. And you can see when the detuning is set to 0, there's actually no impact to the transfer process when we have 0 detuning. And this is actually maybe a bit surprising because it's when we have 0 detuning is when the excitonic states are it's most delocalized. But it turns out there's actually a destructive interference effect that occurs because there is a symmetry at this point. And so there are no coherences generated by the interaction to the environment. And so therefore there is no impact to the transfer rate process. And then we see this increase, as we increase the detuning, you see a suppression effect. And then as eventually we see a crossover into enhancing around where you have the thermal energy scale of this path. And then quickly, I'll also talk about these results now. So I fixed the detuning at 400 wave numbers. And so I have two columns of results here. The first column here is for coupling strength V equal to 10. And then for the other column, it's V equal to 100. And so the reason why I've done it like this is because in the total rate of transfer, you can see that there's an optimal value. So there's where the transfer rate is at its largest. And then we can look at how coherence is influencing the dynamics at this point. And it turns out that it can either be enhancing the rate at this optimal value or suppressing. So it's not really, so for the fact that you have a optimal value here is not so much due to the enhancing or suppressing dichotomy, but rather because there's a modulation of the transfer rate due to the quantum coherence. And just to summarize, I've established a general theoretical approach to quantifying quantum coherent contributions to energy transfer. And this is quite general. You can look at other systems other than the dimer. And this, for the dimer, we've shown that the influence of quantum coherence can be impactful and is important to actually modulating energy transfer. And also, if we want to see coherence having a functional role in the energy transfer process, you need a finite detuning. So you need to stay away from the symmetry condition. So I'd like to thank my funders, Gordon and Bert Moore Foundation, and These are my references. Thank you.